Quantum computation and quantum information are two mathematically comprehensive subjects that form the foundation of our understanding of quantum computers. In this video, we're going to be talking about three important things to understand inside of these two intriguing theories, namely linear operators, the completeness relation, and adjoints. So let's begin without further ado. So in this video, we're going to be talking about these three important things. So let's begin with linear operators. But before that, thanks to the book Quantum Computation and Quantum Information by Michael A. Nielsen and Isaac H. Wong. So let's begin. So what is a linear operator? So we need to define this intuitively by defining what an operator is and then defining what a linear operator is. So let's talk about this. Operator. So let's first decode the word. Operator sounds like we operate on something. Now that's not the exact meaning, but an operator is something that operates. So we know that for sure, but we don't know the exact definition. So right now, let me list it. An entity that produces a specific change on a quantum state. Okay. So, an entity that produces a specific change on a quantum state. This is essentially what an operator is, but now this definition might even make it more confusing. So let's decode this. So an entity is pretty much just an object. Now we can just find this as an abstract entity, so an abstract object. So it's an abstract object that produces a specific change on a quantum state. So let's first define what a quantum state is. Quantum state. Now to learn more about this, please visit my previous videos on quantum computation, quantum information, as well as quantum mechanics, because I talk about what quantum states are on a deeper level. But quantum states are just vectors. Now, vectors are essential importance because they have magnitude and direction. Okay, so let's change this definition. An abstract math tool that produces a specific change on a vector. So right now we've got an abstract math tool that produces a specific change on a vector. Now this definition is much more sophisticated because it is much more concise and much more comprehensive. So sophistication goes in both ways. It has to be simple and concise. So we've got a sophisticated definition of this abstract but also irreducible and hard definition over here. So we've got this, and this is much more intuitive to understand. So it was just a math tool that produces a specific change on a vector. And we've defined what vectors are in countless videos previously. So if you want to learn more about what vectors are, please visit my previous videos. So let's continue. So we have a math tool that produces a specific change on a vector. So what do we have to do to essentially create this into reality? We need to find an example of an operator. Okay, so what is an operator and what is an example of it? So an operator, an example of it is I. Now if you watch my previous videos, this is just the identity matrix. Now, I sub 2 represents the commonly known 2 by 2 matrix, which is 1, 0, 0, 1. So this is essentially just an operator. Now you might be wondering, well, how is it an operator? What does it do? And why is it called identity? Well, as the name suggests, the identity operator, just when applied onto any vector per se, just gives that vector itself. So if we have the identity operator multiplied by a vector, we get that vector itself. Now, notice that this is theoretically we have a 2 by 2 matrix, but we're not including specifications over here. We're just finding what the goal is. So the goal of this is to just produce that. Okay, so now that we've talked about that, we can continue to move on talking about the most important part, linearity. So, in my previous videos, I've talked about linearity a lot because linearity is something that distinguishes quantum mechanics and general relativity. Now, general relativity is a non-linear theory, but quantum mechanics is a linear theory, which makes the mathematics much more easier per se, and also just makes it much more comprehensive. So it is essential to understand what linearity actually is. Now, in my previous videos on this channel, I've talked about what linearity is. So if you want to learn more about that, please go to my previous videos. But let's continue. So, we have an operator, A, and we're applying it on this. And we're saying that this is equivalent to this. Now, if you don't have a deep passion for mathematics, or you just don't have the intuition for it, this might look like complete gibberish, and that's completely fine. And that's what we're going to do next, decode this. So how do we decode this, and what is our main goal of this? Simply what this is saying is it's saying that if we have a sum of terms with a scalar quantity and a vector, or to make it even much more simpler, let's say we have a sum of terms, and these sum of terms have a number and then a vector. Now notice that this just represents vector notation. It's called Dirac notation, and this is the ket vector. So let's just say we have a vector, and we have a number multiplied to that vector, and we have a series. So like 1 times the vector 1, and then 2 times the vector 2, and then 3 times the vector 3, and then etc. Let's say we apply an operator. What we're saying is that if we have an operator, parentheses, and that list of terms I just said, this is equivalent to just the operator distributed on each of these terms. So if you're not an auditory learner, we just have A times A1, B1, plus A2, B2. It's just equivalent to A1, A, V1, plus A2, A, V2, etc. So that's essentially what it is. We're just theoretically applying the distributive property, even though mathematically it's not the distributive property because we're more operating on it. And operating can just be considered multiplication of a matrix by a vector, which I'll explain a little moment later. But pretty much this is what just is. So if you want to have an intuition for it, or you just want to understand on a higher level, you can just consider it as the distributive property. So this is essentially what that is saying. We can just distribute. So A times A1, B1, plus A2, B2 is equivalent to A1, A, V1, plus A2, A, V2, ... So that's essentially what this means. So let's continue with the rest of the video. So we've defined what linearity is and we've defined what an operator is, but we haven't defined what an operator actually is. So what I mean is, we defined the concrete definition for what an operator theoretically is, and we've given an example. But what is an operator? Here's the most important part. Any linear operator can be represented as a matrix, and any matrix can be considered as a linear operator. This is of crucial importance. So when we talk about linear operators in future videos, we mean a matrix. And when we talk about matrices, oftentimes we mean linear operators. Because a linear operator can be written as a matrix. And this is a highly sophisticated definition because if we have a linear operator applied on a vector, we just know that this is just a matrix times a vector. And if we know if it's a 2x2 matrix, a square matrix, or whatever, most likely it's going to be a square matrix, and we know what the vector is, we know what the dimensions of the result is going to be. So an operator is just a matrix, and a matrix is just an operator. But it's essential to realize that there are two discrete subjects, two discrete entities per se. A linear operator is not a matrix, but a linear operator can be represented by a matrix, and a matrix can be represented by a linear operator. This might sound confusing at first, but mathematically this is what is true. Okay, so let's move on to the next part of our video. Okay, so we have linear operators, and we've just done that, so check. So what is the completeness relation? So the completeness relation is just this. If we have the sum, and we have I, and we have this, I, this is just going to be equivalent to the identity matrix. So this is the completeness relation. This is something called the outer product. Now we have inner products, which is just this. This is called an inner product, and I've talked about this in my previous videos on this channel. And notice that in quantum mechanics we have anti-symmetry or anti-linearity, and that it doesn't satisfy the full properties of, let's say, like dot product in a regular vector space. But that is of a tangent right now. So an inner product looks like this, and an outer product looks like this. So this is not an inner product, this is an outer product, but this is how an inner product looks in comparison to this. This is an outer product. Okay. So, why is this useful in the first place? The reason it's useful is because we can pretty much just construct a different representation. In mathematics, oftentimes, when we have proofs or when we have different types of mathematical expressions that we're trying to solve, oftentimes we need substitutions. Now, these substitutions are crucial because when we imply or apply a useful substitution onto something or into something per se, we will get a useful result, and this result will be used a lot in future times. So let's say you're working through this hard math problem and then you find the completeness relation might work because you can apply the outer product. You do it, the problem becomes much simpler, or it might seem complicated at first. You simplify the expressions and you get the result nice and clean. So that's what the completeness relation is useful for. Second, there's something called product states, or not product states. More specifically, we have projections or projective matrices. Now these projections or projective matrix in definition uses this. So the definition of a projective matrix uses the completeness relation. So oftentimes when you're dealing with projections, orthogonal projections per se, and you're working out huge mathematics of that, and then you have this, you can use the completeness relation for a projective matrix, substitute for that, and get the result. So this is of crucial importance because we know that now if we take a sum like this, so like I, so that's like 1, 1, plus 2, 2, and then etc., we're going to get the identity. And that's what it essentially means. Now, notice that it depends on how you represent the two vectors. Oftentimes, they're not represented by twos, and sometimes they are. So it's just a little complicated at first. But what it's just saying is if we have a sum of terms like this, and ranging from consecutive order, we will get the identity matrix when we add an infinite amount of them. Okay, so now that we've talked about the completeness relation, we have the last thing, which is of crucial importance as well, which is the adjoint. So an adjoint is very important due to the fact that it's also used like a linear operator. So an inner product, so let's say we have an inner product from a vector v and then a vector w. And let's say we have a vector or an operator, linear operator, applied on w. Now, what we're going to try to do is we're going to try to essentially make this equivalent expression, but moving the linear operator. So let's say we have v and w. We want to make this equivalent to something v, comma, w. Now this is just an example of inner product notation we're just using over here. How do we do this? Well, we use this via the adjoint. The adjoint is essentially just the conjugate transpose. So conjugate transpose. What we're doing is we're taking the transpose of the linear operator, which can be expressed as a matrix. So we're essentially taking the linear operator, putting it into matrix form. We're taking its conjugate, complex conjugate, which means that we're negating the i's. So what means if we have I, this becomes negative I. If we have negative I, this becomes positive I. And then real numbers just become real numbers. So once we do the conjugate, we're going to have the transpose. The transpose is just transposing a matrix. We're just switching the rows and columns. And that's what we have the adjoint. So A represented by a dagger or A represented by a star. Now notice depending on if you're a physicist or mathematician, the notation changes, but they just mean conjugate transpose. And this is called the Hermitian adjoint when A is equivalent to A star, which can also be called a self-adjoint. Notice that they have discrete definitions. So the self-adjoint and Hermitian adjoint are two different things, but we can, in a sense, just generalize them to being the same thing because we don't really care about the specifics. So when we do care about the specifics, they're different. But right now, if we're just doing it as a whole, we can just consider it to be the same thing. So Hermitian adjoint, also called as a self-adjoint, excluding the minor discrepancies, just means that A is equivalent to A star, which I mean A is equivalent to the conjugate transpose. And that means that when we just do this, this is equivalent to AV, comma, W. So they mean the same thing, if this is true. Okay. So now that we've talked about adjoints, we've talked about the completeness relationship and linear operators, we can make this video to an end. Now, it's essential to understand that these three concepts form the foundation of primarily most things in quantum computation and quantum information. So we can make this video to an end. If you like this video, if you like this channel, please subscribe to learn more. Thank you.